Welcome to Chapter 10, Binary Search Trees. A binary search tree keeps its keys in order. At every node, smaller keys sit on the left and larger keys sit on the right. You will learn to search, insert, and delete. The speed depends on the tree's height. A balanced tree is fast. A skewed tree is slow. Let's start with why a binary search tree is worth building. We will take a game you already play well and turn it into a fast search structure. Chapter 9 showed the shape of a binary tree. This chapter adds just one rule, and that rule turns the shape into a fast search structure. This is what you will be able to do. First, you will state the ordering rule. At every node, the left side is less than the node, and the node is less than the right side. Second, you will trace search and insert. You start at the root, compare, and follow one branch down the tree. Third, you will validate a tree. You will tell a correct ordering apart from a broken one. Fourth, you will pick the right delete case. A node can be a leaf, have one child, or have two children, and each case is removed a different way. And fifth, you will explain the height trade-off. You will see why the same set of keys can make a fast tree or a slow one. One idea drives the whole chapter. Left is less than node is less than right everywhere. With that rule in place, every comparison throws away one whole subtree. You never look at that side again. And if the tree stays balanced, the subtree you threw away is about half the keys that were left. That is where the speed comes from. Think back to the higher or lower guessing game from Chapter 1. It runs the same idea we need here. A friend picks a number from 1 to 100. You guess, and they tell you too high or too low. Each answer throws away half of the numbers that are still possible. You guess 50, then 75, then 62, and you win in about 7 guesses. You never need 100 tries. Every too high or too low is one comparison with 2 outcomes. Go left or go right. Now draw that game as a tree. Each guess is a node. Too low sends you down the left branch. Too high sends you down the right branch. A binary search tree is just that game's decision tree, and the stored keys are the guesses. This only works if the tree was built in sorted order. If it was not, then go left for smaller points at the wrong branch, and the game leads you the wrong way. Let's look at the same rule from a different angle, a choose-your-own-adventure book. Every page holds one number and one instruction. The instruction says, if your number is smaller, turn to the left page. If it is larger, turn right. You never flip back, and you never read the pages you skipped. You follow one straight path to your answer. Finding a value is just following the turn here arrows until the page matches your number. Search visits one page per level, never the whole book. You get the same speed as the guessing game. It works because the book was printed in order, so every arrow points the right way. This breaks down if the book was bound out of order. Then you follow turn left for smaller and reach a page that sends you further from your value, not closer. Chapter 9's binary tree has the shape, a root, children, and subtrees, but it has no rule about which values sit where. So when you look for a key, you get no hint to go left or go right. You must check nodes one by one until you find it or run out. Watch it search this tree for 6. We check the root, which is 7. That is not 6. No rule tells us which way 6 would be, so we cannot throw away either side. We turn 7 gray to mark it checked. We move to 7th left child 2. 2 is not 6 either. We check 14, still not 6. We check 5, still not 6. Now the whole left side is gray, none of it was 6. So we try the right side. We check 11, not 6. We check 1, not 6. We check 9, the last node, not 6. Every node is now gray. 6 is not here. That was 7 comparisons for 7 nodes. Big O of n, no better than a linked list. So the branching gave us nothing. With no ordering rule, we still checked every node. We already have the two-way fork that the guessing game needs. The shape is not the problem. What we are missing is the rule that says which fork holds the key. That rule is the binary search tree. It is the whole of this chapter.